Okay, so this is kind of a summary sheet of the states of matter and the gas laws review. So you should be looking through your notes, getting your reference tables out, calculator. This kind of summarizes everything. Okay, so solids, liquids, gases. First of all, the shape. The shape of a solid is definite. The volume of a solid is definite. The forces or intermolecular forces, intermolecular attractions, they're very strong. And if you were going to identify them in a particle diagram, super close together, bunched up towards the bottom. Liquid, variable shape. That's why you can pour water into different shapes of an ice cube mold, and you put it in the freezer and it stays. Volume, that is definite. That's going to stay. Forces are medium, moderate, and your particles are going to be a little bit further apart this time. Gas, variable shape. You can have different shaped balloons full of helium gas. Volume, gases take the volume of their container. Very weak forces, and the particles would fill that. Standard pressures. So these are found on the reference tables. So here we have, let's start with, here we go, right here. Standard pressure. It's 101.3 kilopascal and 1 atmosphere. And then the honors section is, sorry to make you dizzy, 760 torr and 760 millimeters of mercury. So going back to this, 1 atmosphere, 101.3 kilopascal, 760 torr, and 760 millimeters of mercury. So these are on the regents, and these are honors only. So not on the regents, just for my honor students. So if you ever need to convert pressures, always, you're given multiplied by what you seek over what you know. So 825 torr to atmospheres. 825 torr is what I have given. I seek atmospheres, and so our standard is 1. I know torr, so 760. Torr cancels out. So let me get my calculator out. 825 divided by 760 gives me 1.0855, etc., which, if you're rounding to sig figs, would be 1.09 atmospheres. Okay, entropy. Entropy is defined as chaos, disorder, or perhaps mess. Nature favors high entropy and low energy. So think about, an overgrown lawn after a month vacation. So the lawn just grows crazy. That's what nature favors. This is called the phase change diagram. A lot of this is already provided, but what you do need to know is the formulas you need to use and when. So, and also this way where you go solid to liquid to gas, this is endothermic. You're taking heat in. If you were to read the graph this way, you'd be exothermic, which is a gas to a liquid to a solid. All right, but back to this. Anytime you see an increasing line that's like diagonal, that's going to be Q equals MC delta T. Because, as you notice, the temperature changes here on the Y. MC delta T. Sorry, it's messy. Q equals MC delta T. What else you need to know is during these periods of time, you have a change or an increase in kinetic energy. Increase in kinetic energy. So you'll notice if you ever had to calculate, you'd say, a solid is being heated from, 5 degrees Celsius to 10 degrees Celsius, and it has a mass of 25 degrees, what is the heat absorbed? So you would just do your delta T, and don't forget that delta T is equal to T final minus T initial. Because you might get questions where they might ask you for just the T final. All right, so we got solid is here, and solid goes to liquid that's called melting, and the reverse is called freezing. And if you notice, to take this all the way over to the Y, you see the melting point, but it's also the freezing point. Those are, the same temperature. And during that period of time, you have an increase in potential energy. So when we have our Q formula, you don't have a delta T. So going back to your reference tables, table T, sorry. Oh no. So, oh boy, sorry. If I go back to table T, I cannot use delta T here. So I have MHF and MHV. Yeah. So Q equals MHF, the heat of fusion is between solids and liquids. So this is melting or freezing. Heat of vaporization is boiling or condensing. These are constants found on table B. So coming back, table B. I'm going to erase this. So here we have our heat of fusion and our heat of vaporization constants. So going back to this, if you are freezing and melting, this is Q equals MHF. And again, this is an increase of potential energy. This is Q equals MHV. And, melting is solid to liquid, vaporizing, or boiling this way. Now, the phase changes that I didn't include would be solid straight to gas. That's called sublimation. And things that sublime are dry ice, which is solid carbon dioxide going straight to CO2 gas, and also mothballs, which are naphthalene. And the opposite of that would be gas straight to a solid, which is called deposition. And that is candle smoke or char in the fireplace. Yeah. So if your substance is water, HF and HV constants are found in table B. If your substance is not water, it would have to be, those would be provided to you. All right, so now using some calculations. 16.8 grams of water is at 0 degrees Celsius. How much energy is required to melt it? So keywords, 0 degrees Celsius and melt. So Q equals, I don't have a temperature change. So I have instead heat of fusion, because that's what happens with melting. So Q, well, I don't need to change that. 16.8 is our mass. And our heat of fusion is, if you look on table B, 334 joules per gram. So let's do that. 16.8 times 334. 5611.2. And so if you were to take your sig figs, it'd be 3. So that would be joules. So 3 sig figs is 5610. 5610. 215 grams of water is undergoing a phase change from liquid to gas, 100 degrees Celsius. How much energy is required to make this change? So those are indications that we've got heat of vaporization. So 215, heat of vaporization constant is 2260 joules per gram. 215 times 2260 gives me 485,900. Looking at your sig figs, there's going to be 3 because of 215. So 486,000 joules. Again, technically, if it's a Regents question and they don't ask for sig figs, you don't have to do it, but you know me, I want them. 4.850 grams of water is heated from 15 degrees to 25 degrees Celsius. How much heat was absorbed? I see a temperature change, so I'm going to do Q equals MC delta T. 4.850 times specific heat is 4.18 joules per gram degree Celsius. T final minus T initial, which is the same as 10. So 4.850 times 4.18 times 10 is 202.73 joules. And this is 4 sig figs. This doesn't count for sig figs. This is 3 sig figs. So 3 sig figs would be 203 joules. Definitions. Hygroscopic means absorbs water from air, such as sugar clumping up. Deliquescent means it can dissolve itself from absorbed water. And there are very few substances that do that. We talked about anhydrous calcium chloride. Okay, specifically about gases, kinetic molecular theory. Gases can be compressed because they have lots of space in between. They have elastic collisions, meaning once they collide, they're not going to change forms of energy. They have no attractive forces. But the most important one that you should know is that they move in random straight line motion. That's probably the most important one you need to know. Pressure, which is when particles bounce against each other and the walls of the container. That's a force divided by area. That's pressure. Our amount of a gas, volume, and temperature. So as the amount of a gas increases, you're going to increase your number of collisions, which means therefore, therefore, increase your pressure. So this is a direct relationship. Your volume. If you increase your volume, you're going to have more space, which means you're going to decrease collisions and therefore decrease pressure. Similarly, if you were going to decrease the volume, you would increase collisions. I can't spell. Teeny tiny eraser. There you go. You would increase collisions and therefore increase pressure. So this is an inverse relationship. Temperature, if you are going to increase the temperature, particles are going to move faster, so they'll have more collisions and increase the number. So therefore increase the pressure. That's a direct relationship. Okay, so let's talk about the gas laws. First of all, specifically knowing who Boyles and Charles' law is not super important. What you do need to know is that on the reference table, there is, on table T, combined gas law. Combined gas law, it's right here. P1 V1 over T1 equals P2 V2 over T2. P is pressure, V is volume, T is temperature. 1 means original conditions. 2 means conditions after a change. P can be in any unit for pressure, so kilopascal, atmosphere, torr, millimeters of mercury. Volume could be milliliters or liters. The only thing is temperature must be in Kelvin. It has to be because it's an absolute scale. So similarly, if you ever given degrees Celsius, you can just convert right here. So if anything is constant, you just cover it up. So for example, if the question says a constant temperature, you would just get rid of this and there's your formula. If the question said a constant pressure, you would get rid of this and there's your formula. So you can come back to combined gas law. So back to this. Boyles Law is where temperature is constant. So this is P1 times V1 equals P2 times V2. And this is an inverse or indirect relationship. So temp is constant, so you do not include it in your formula. A 15 liter sample of gas is at 2.5 atmospheres. If the pressure increases to 3.9 atmospheres, what's the new volume? So I usually read the question. A 15.0 liter sample of gas is at 2.5 atmospheres, period, which means it's originally, this is my pressure, this is my volume. But now the pressure increases to this, so what's going to happen here? And you can call that X if you'd like. So let's do this math. 2.5 times 15.0 is 37.5 equals 3.9 times V2. Divide both sides by 3.9. V2 is equal to 9.61538, etc., etc. So it doesn't tell me how to round but if I did sig figs, this is 3, this is 2, this is 2. So 2 sig figs would be 9.6, and then my units are liters of volume. Liters. Charles's law has constant pressure. So this is V1 over T1 equals V2 over T2. This is a direct relationship, meaning as one goes up, the other also goes up. And this has to be, of course, temps in Kelvin. And if you don't remember, degrees Celsius plus 273. It's on table T. 2.8 liters of gas is at 280 point Kelvin. If it's cooled to 265 Kelvin, what's the new volume? So volume 1, temp 1, volume 2, temp 2. So cross multiplication works good for me. So 2.8 times 265 is 742 equals 280 times V2. Divide both sides by 280. V2 is equal to 2.65. And this has 2 sig figs, 3 and 3. So 2 sig figs would be 2.7 liters. Combined gas law is everything. It's P1 V1 over T1 equals P2 V2 over T2. Let's change it up. Okay, so original sentence says 102.8 kilopascal, 26.5 liters, 265 Kelvin. Pressure decreases to standard. Well, standard is 101.3 kilopascal. So why can't I call it 1 atmosphere? Because I'm already in kilopascal. Volume 2 is what we're looking for, and this is 240 Kelvin. So 102.8 times 26.5 times 240 gives me 653,808 equals 265 times 101.3 is 26844.5 times V2. Divide both sides by this crazy number. 26844.5. All right, now I got to plug it in. 653,808 divided by 26844.5. And I get V2 equals 24.355. Talking about sig figs, 3, 4, 3, 3. Looks like 3 sig figs. 24 point, this rounds this up, 4 liters. Woo! Okay, ideal gas law. This is honors only. Okay, so only my honors students need to worry about this one. I'll provide you the formula, which is PV equals nRT. P, V, and T you should know. N is number of moles, and R is a constant. If pressure is kilopascal, you're going to use 8.31 for a value of R. If pressure is atmospheres, you're going to use R equals 0.0821. Now, you're not going to need to memorize that because they are on this R, universal gas constant. So here's atmospheres. Now, this is kilopascal, that bottom one. Anyways, you can always convert everything to atmospheres if you'd like. So there's that. Now, I was a real brat because I made you have to convert everything. So P is, it says 900 torr. So over here, 900 torr, I want either kilopascal or atmospheres. I'm going to go atmospheres. I seek atmospheres. I know torr. So goodbye to those. 900 divided by 760 gives me 1.184 kilopascal. V is 750 milliliters, which I can't use milliliters. I need liters because R is in liters. The units for R are kilopascal or atmospheres times liters over moles Kelvin. So I got to do 0.750 liters. N is what I'm looking. No, I'm not looking for N. So over here, it says 5 grams. Well, how do you go from grams to moles? Oh, I divide by GFM. GFM is, what is it? Oh, 35? Let's just check it out. Sorry, I had a total brain freeze. Chlorine is 35, and let's 35 times 2 because it's Cl2. So 35 times 2, 70. I haven't even gotten to the formula yet. 5 divided by 70 is 0.0714 moles. 0.0714. And then the R value we're going to use, we're going to do atmospheres. So it's 0.0821, and then temperature. Woo! All right, so 1.18 times 0.750 is 0.885. 0.0714 times 0.0821 is small number 0.0586 times T. And I'm going to divide both sides by that. So 0.885 divided by 0.00586 gives me 151.02, etc. That's got 3 sig figs, 3, 3. So 3 sig figs. So we're going to look at 151 Kelvin. Now that's a real crazy question. I'm not going to make you do all that different converting. Real gases, this is like the beach. High temps and low pressures. Home stretch here, table H. So, the stronger the intermolecular forces, it's going to be the higher the boiling point and the lower the vapor pressure. And this is because you're holding your particles together tightly, and it's going to take longer for them to spread out and boil. And there'd be fewer of them being particles that are bouncing around. The weaker the intermolecular forces, the lower the boiling point and the higher the vapor pressure. When vapor pressure equals atmospheric pressure, the substance will boil. So here is standard pressure. So anywhere these 4 curves hit that, just travel down. That's not straight, sorry. And you'll find their boiling point. Boiling points are temperatures. Dalton's law of partial pressures. This is honors only. In a mixture of gases, the total pressure of the mixture is equal to the sum of each of the individual gases' pressures. When the total pressure exerted by a mixture containing two gases, what is the total pressure if the one gas is 70 kPa and the other is 30? Well, gee, what's the total? 100 kPa. And finally, honors only, Graham's law of effusion. Sometimes I call it diffusion. So I will give you this formula on the test. Lighter gases diffuse faster than heavier gases. That's important to know. So then we'll say, under the same conditions of temperature and pressure, how many times faster will hydrogen diffuse compared to carbon dioxide? So hydrogen, CO2. We need GFMs. GFM is 1, but there are 2 of them, so that's a 2. 12 plus 16 times 2 is 32, 44. So you need square root of heavy over light. So we're going to get the square root of 44 over 2, which is going to be the square root of 22. So let me do that right now. Flip my phone calculator to the side. Square root. I believe it's 4.6. So what does that number mean? That means that hydrogen will diffuse 4.6 times faster than CO2. And you could also say CO2 will diffuse 4.6 times slower than hydrogen. So I'm going to give you this formula, but you're going to need to know this part. Okay? That's it. So if you've got any questions, let me know. Thank you.